So this is going to be our final section on convergence tests, or new convergence tests at least. So first off, before we actually get into a discussion of the tests themselves, there is some new notation that we need to go into. So, given a series, we can consider the series of absolute values. So, the series that you get if you just replace the terms of the series with their absolute values instead. A series is said to be absolutely convergent if the series of absolute values is convergent. And, as it happens, you can show that if the series of absolute values is convergent, then actually the original series is convergent as well. A series is called conditionally convergent if it converges, but the series of absolute values does not converge. Okay? So if the series of absolute values converges, then the series converges. But if the series of absolute values does not converge, well, that doesn't say anything about the original series. It might still converge, in which case it's called conditionally convergent. So, any series that you look at is going to either be absolutely, conditionally convergent, or neither of these. So here's a few examples. So here we have an alternator, but aside from the alternator, it's just the series of reciprocal squares. Now, to see if this is absolutely convergent or not, let's look at the series of absolute values. So, literally just take the absolute values of all of the terms. And really, the only effect that that's going to have is going to be to kill the alternator, right? Because the alternator, this dude on the top, is what's making the sign change from positive, negative, positive, negative. So if you take the absolute values, that means it's always going to be positive. Like so. So what about this dude? Well, we know that this converges because it's a p-series with p equals 2, greater than 1. So, because of that, we conclude that the original series is absolutely convergent. Okay. So yeah, taking the absolute values just kills the alternator. Well, similar thing's going to happen here. Here we have an alternating harmonic series. Well, we know that this guy converges. So by the alternating series test. But it is not absolutely convergent. Because if you take the series of absolute values, well, that's going to kill the alternator, in which case we just get an ordinary harmonic series, and those are known to be divergent. So, because this guy converges, but does not converge absolutely, that means that it is conditionally convergent. That is what conditional convergence means. So it's conditional on the fact that you uh, keep the sign structure the same. Okay, what about this dude? Well, this dude doesn't have an alternator, but it does have a trig function in it. And trig functions can sort of behave like alternators in the sense that, the sine and the cosine, they're waves, so they're always going between positive and negative. So, to see if this is absolutely convergent, let's look at the sequence of absolute values. Or the series, rather. Oops. Okay. Well, what can we take from this? Notice that the cosine is always going to be between -1 and +1, right? Right? So if we take the absolute value of cosine is always going to be between 0 and +1. So that means that this series here with the absolute values is guaranteed to be less than or equal to the series you get where instead of cosine on the top, you have 1 on the top. Now, this latter series converges because it's a p-series, so that means that the series of absolute values also has to converge by the direct comparison test. So we conclude that this dude, the series of absolute values, converges by the direct comparison test. Hence, this guy is absolutely convergent. I wonder why sometimes it copies the formatting on the sum and sometimes it doesn't. That's kind of annoying. Anyway, so why would we care about this? I mean, this seems like a completely arbitrary distinction, right? Well, first off, it is occasionally a useful tool to determine convergence. I mean, I wouldn't really know how to go about attacking convergence of this guy directly, but if we put absolute values around it, then we can make this comparison. Hence, this guy is absolutely convergent, and if something converges absolutely, then we know it converges. So this notion of absolute convergence does give us another avenue for determining convergence, because it allows us to put absolute values around things, and that putting absolute values around the terms of the series might make it look a lot simpler. More deep than that, though, absolute convergence is a stronger, quote-unquote, stronger condition. There's a really remarkable fact due to the famous mathematician Riemann, so the same Riemann as in Riemann sums, that states that if a series is absolutely convergent, then we can rearrange the terms of the series in any way we wish without changing the sum. So that's to be expected, right? I mean, we know that addition is commutative. That means that if you're taking a sum of a big string of numbers, it doesn't matter what order you take the sum in. So what's surprising is that infinite series don't necessarily enjoy the same flexibility. If an infinite series is absolutely convergent, then yes, we can rearrange the terms, and that doesn't change the sum. But remarkably, if a series is only conditionally convergent, then rearranging the terms of the series might change the value of the sum dramatically. In fact, we can make the sum be any number we want just by rearranging the terms. We can even rearrange the terms to make the sum diverge. So, conditionally convergent series are very, very fragile. The thing that they converge to is completely dependent on the order in which you take the sums. The order in which, the summands are arranged. Whereas absolutely convergent series behave more like we would expect, where you can just take the sum in any order you want. So that's a very interesting thing to point out, and it's one of the ways in which infinity and computations involving limits and infinity really don't necessarily behave the way that you would expect them to. Okay, so with that definition out of the way, here's the real meat of the section today, the ratio and the root tests. Alright, so for a little bit of motivation, recall that when we were talking about the limit comparison test, the idea was that a given series might be eventually indistinguishable from another series. And the way that you would say that formally is that the limit as n goes to infinity of the ratio of an to bn is eventually a constant. But really what we are claiming is that if a series is eventually like this series, then they should have the same convergence behavior. The basis of these tests is the same idea, but now, instead of taking a series and comparing it to some arbitrary series that we have to come up with, we are going to take a series and compare it to a geometric series specifically. Because geometric series are very nice. Their convergence properties are easy to determine. So if the series that we are looking at is eventually indistinguishable from a geometric series, that's some very useful information to have. So that is what these tests are going to try to determine. Right? It's going to determine whether the series you've been given is eventually indistinguishable from a geometric series or not. So, recall, geometric series have this form, where a and r are constants. A has to be non-zero, because if a is 0, then you just have a series of zeros, and that's trivial. And this guy converges if the absolute value of r is less than 1. Now, this number r is called the common ratio, because if you take any two adjacent terms of the series and divide them, their ratio is r, right? I mean, take the n plus 1th term and divide it by the nth term. So if the general term is n minus 1, the n plus 1th term is going to be ar to the n, divided by ar to the n minus 1. So all of that cancels except for 1r, right? So if you were just given a generic series, the way that you would be able to tell that this guy is geometric is if the ratio of subsequent terms is always constant. Okay? So a series is geometric if and only if the ratio of subsequent terms is a constant. In particular, a given series is geometric and convergent if and only if this ratio of terms is constant and the absolute value is less than 1, right? That's exactly what it means for it to be convergent. So, we are concerned with whether our series is eventually geometric or not. So what does that actually mean in terms of this right-hand side over here? Well, this series is eventually geometric and convergent if and only if this term is eventually a constant which is less than 1. Well, How do we translate the word eventually into mathematics? By taking the limit, naturally. So, since the convergence of a series is only dependent on what it eventually looks like, you can cut out the first billion terms of the series and who cares? Convergence is an asymptotic property, so convergence is only dependent on what the series is eventually doing. It stands to reason that the convergence or divergence of a series might be determined by this number here. In particular, if this number is a constant which is less than 1, then it stands to reason that our series is going to be convergent. And indeed, that is exactly what the ratio test says. So given a series, let L be this limit. So it's the limit of the absolute values of the ratio of subsequent terms. If this limit exists and it is smaller than 1, then that means this guy is eventually a convergent geometric series, and therefore it converges. And more than that, we can actually say that it's absolutely convergent. If this limit ends up being larger than 1, or infinity, well, then it diverges. Because remember, if this absolute value of r is larger than 1, then the geometric series diverges. So it's the same reasoning here. Now, if this limit actually ends up being equal to 1, then we actually can't conclude anything. Because, for instance, consider the series, the ordinary harmonic series, and the p series with p equals 2. If you just go ahead and compute this limit, you can find that L is equal to 1 for both of these guys. That's an easy enough thing to compute on your own if you don't trust me. But this dude diverges and this dude converges. Okay? So the fact that this limit is equal to 1, that means that we can't conclude anything. The series might be convergent or divergent. Okay. So for an example, here we've got this series. Test this for absolute convergence. So, well, we're going to use the ratio test, because the ratio test is capable of giving us absolute convergence. So, we need to compute this limit. Okay, let's see. So what is the n plus 1th term? Well, that's what you get when you replace n with n plus 1 in all of this mess. Careful about your parentheses here. And then the nth term is just that. All right, so there's a lot of simplification that can be done here. It's an ugly expression right now, but I think it'll simplify pretty nicely. First off, notice the absolute values are going to kill the alternators. So we can just throw the alternators away. And we can throw away the absolute values also, because with the exception of the alternators, everything else is clearly positive.